Hello everyone, welcome to part 3. In this part we are gonna try to find the structures of hydrocarbon 1 and 2. Let's get started. So now we have a structure for compound 3, and if we number from here 1, 2, 3, 4, 5, it's gonna be 5, 5 dimethyl cyclopenta 1,3-diene. That's the name, IUPAC name for this compound. So because the question asks us to find the structure of compound 1 to 3 and A to J, and we found all ciphered compounds in the previous slide, but we only found compound 3, which was the last compound of the synthesis, but we didn't find the structure of compound 1 and 2, and that's what we are gonna do right now. So the only information that we have is that hydrocarbon 1 is homologue of compound 3, and it dimerizes to hydrocarbon 2, and that's the only information we know, and we also know their boiling points. And actually this is the only thing you need, because if you go back here, we have the original problem in the previous slide that we showed last time, and then here we have compound 3. We got it through the synthesis, and there's no any other piece of information in order for us to find the structures for 1 and 2. It's only this part, and we have converted this part into a diagram form, so we are going to use the same diagram. Unfortunately, in compared to previous case where we had a full synthesis, we have set of reagents and sometimes molecular formula and some other piece of information that could help us in order to find out the structure of molecules. In this case, we don't have a lot of information. Unfortunately, we only are given this bunch of sentences, which we converted into diagram form, as you can see here. But other than that, we don't have any information, so we have to see what we are given. So this is homologue. So what is homologue? Homologue means the series of compounds that differ from each other by two groups. You add CH2, you get another homologue. Add another CH2, you get the next homologue, and so on. So we know that we don't have any other functional group. We don't have to introduce any other atom. So this is just one CH2 more or less, or maybe multiple CH2s more or less. For example, methane, ethane, propane, butane, and so on. They are like homologues of each other because every single time you are adding one CH2 group. So now we know that it's homologue, so we can go maybe one carbon less, keeping the similar structure, one carbon less. Maybe we can remove one methyl group here. That's one possibility. Or we can add another methyl group somewhere here. That's also homologue. But one key piece of information here is that boiling point of compound 3 is higher than boiling point of 40. So hydrocarbon 1 should have less number of carbons in compared to compound 3. So why this is the case? Because these physical properties like boiling point, conductivity, crystal structure, and so on, these properties are directly related to intermolecular interactions, which in turn are dependent on many factors, including molecular size. So there's no a direct relationship between number of carbon atoms and the boiling point. So there is something in between, and that is intermolecular interactions. So stronger the intermolecular interactions are, higher the melting and boiling points will be for specific compound. For example, that's why alcohols have higher boiling point in compared to the molecules that have the same molecular formula but have ether functional group, because ethers do not have hydrogen bonding, but alcohols do have hydrogen bonding. When you have hydrogen bonding, it means there's higher intermolecular forces. It's going to be much harder to break those intermolecular interactions to send molecules from liquid state to gas states, in other words, to evaporate them. So that's how we set up the relationship between physical properties like boiling point with intermolecular interaction and then molecular size. So here, because this compound is not polar, also it doesn't have any electronegative atom and electropositive hydrogen atom, so we don't have any hydrogen bonding, we don't have any dipole-dipole or ion-dipole interaction. So the only interaction here is van der Waals interactions, or you can call it London dispersion forces. And London dispersion forces are dependent on two factors. First, molecular weight. Higher the molecular weight, stronger the London dispersion forces, higher the boiling point will be. Second factor is surface area. If two molecules have the same molecular weight, then we have to take a look at their surface area. So in this case, because this is homologue, obviously we are going to have different molecular formula and different molecular weight. So we need to find something that has less number of carbon atoms, like lower molecular weight. So in this case, we can think of two possibilities. One possibility is just we remove one methyl group and we are left with something like this. Or we can be like this, just two methyl groups. We can go lower than that, but then we have to destroy the ring structure, so that's no longer homolog. We are going some another function group or something like this. So basically, if we narrow down our search space, we only have two possibilities here. There's actually one very strong evidence here why we are gonna choose this as our hydrocarbon 1 rather than this, because this one, methyl cyclopentadiene, exists as a mixture of isomers. So we dimerize hydrocarbon 1. If we think that this is 1 and we dimerize it, we are gonna get actually multiple products. So because this itself exists as a mixture of isomers. And why it exists as a mixture of isomers? It is because 1,5-hydride sigmatropic shift. So this compound, as you can see here, has hydrogen. So what can happen is this can move here, this moves here, and this moves here. So this is one of sigmatropic rearrangement where your electrons are moving around the cycle. So we call this as a pericyclic reaction. So what could happen is we can get another isomer of this compound, which would have methyl group and double bond in a different position. So a double bond will be here, methyl will be here, and this will be here. So if we can name this as 5-methyl cyclopenta 1,3-diene, okay, we just number it 1, 2, 3, 4, 5, then it's 1,3-diene and with methyl in 5th position. But this one is 1, 2, 3, 4. It's the same 1,3-diene but 1 methyl. Okay, this is called 1,5-hydride sigmatropic rearrangement. This is one class of pericyclic reaction. Actually, Diels-Alder reaction itself is also pericyclic reaction. Like you have this diene and you have alkene. This moves here, this goes here, and you end up with pi bond and 2 sigma bonds forming at the expense of 3 pi bonds breaking. This is also one example of pericyclic reactions. And this happens in just room temperature. So you don't need to have elevated temperature or something like that. So if you have 5-methyl cyclopentadiene, it's gonna isomerize to 1-methyl or even 2-methyl. You can have many rearrangements, so you will get isomers. So if you choose this compound as your hydrocarbon 1, it's basically impossible to have because it will have its isomers as well. When you have dimerized them, you will actually have many dimers. Okay, does not make sense within the context of this question. Now we know that we cannot propose this compound as our hydrocarbon 1, so I would go 1 carbon lower and I would propose this cyclopenta 1,3-diene as my hydrocarbon 1. And so since we have found the structure of hydrocarbon 1, the next part is easy. We are going to dimerize it. So what's going to happen is intermolecular Diels-Alder reaction, but between the molecules of the same compound, same hydrocarbon 1, and we are going to get this compound, and I will show you how we will get this one. So in Diels-Alder reaction, just as I showed you before, you should have this and this. So this is alkene part, and this is diene part. So basically, ene and diene, they come together, they make a cyclohexane ring. Here, this compound will actually act twice, once as a diene, once as ene. I'm gonna write both of them at the same time. So this is in diene form, and I'm gonna write the same thing, slightly rotated form, at it's using its ene part. Okay, then we are gonna have simple reaction. The double bond will move here, this will move here, and it's hard for you to visualize. Just think of it like this. So 1, 2, 3, 4, 5, 6. So we are gonna make a 6-membered ring, and that's this here. 1, 2, 3, 4, 5, 6. If you want, you can even number, right? So let's do this. 1, 2, 3, 4, 5, 6. And this is 1, this is 2, this is 3, 4, 5, and 6. And that makes perfect sense, right? Because I have a new bond between 1 and 6. I have new bond between 1 and 6 and 4 and 5. So 1 and 6 and 4 and 5, these are my new bonds. And I am making a new pi bond between 2 and 3, which is reflected here, 2 and 3. So when you number things, you don't even have to put these are not IUPAC number. You can even put ABC or XYZ, whatever you want, as long as you can track which atoms are in the reactants and then in the products. When you do that, it becomes easier. And as I can see, there is this part that's like that's connected to 1 and 4 at the same time. So you see, I have this carbon atom, I call it as bridge, connected to 1 and 4 at the same time. And then the rest of the compound that comes from alkene part, it's here. So if you just number it in this way, it becomes much easier and you can easily get the structure of dimer. So now we found everything from A to K and compound 3 as a part of synthesis with some bit of judgment. And we found hydrocarbon 1 and we do Diels-Alder reaction, dimerize it to get hydrocarbon 2. And actually 2 can also go back to 1 with retro Diels-Alder reaction. So we call it retro Diels-Alder reaction. Happening here is that we just put the arrows in reverse order. Okay, we will just do this. So this will go here. This is called retro Diels-Alder reaction. So I'm gonna reconstruct 2 cyclopentadiene again. Okay, so if we go back to original question, now we have solved part 1. So it took us a lot of time, but finally we were able to find out all the structures of sulfate compounds as well as hydrocarbons 1 to 3. And we have 3 more questions to solve, so stay tuned for other parts and we will go through them together. Thanks for your attention.